Today I wanted to show a video from the Joe Rogan experience where he had on a climate skeptic as his guest. And I am quite a big fan of Joe Rogan's, actually. I like that he has heterodox thinkers on, and I think that's important even for things like climate change, right? I think it's good that there are people pushing back, even though I personally agree with most of the science describing climate change. I think having people like this is always important in basically any discussion, even if it is sort of settled science. I think you need a scientific community that's willing to address criticisms. So the guest he has on is a very smart guy. Actually, let's just play the part where he talks about his credentials.
First of all, your credentials. You graduated from high school at 16. You went to MIT.
Caltech first.
Caltech.
I was an undergrad at Caltech, and then I went to MIT. I did a PhD there in theoretical physics in 3 years. And then I went back to Caltech, where I was on the faculty for 30 years.
And you were on the faculty at 23 years of age.
That's correct.
Pretty extraordinary.
Yeah, it's unusual, not unprecedented, but really quite unusual.
Now, there's a couple criticisms that people have of you, just to get these out of the way right away. One of them is that you used to work for BP.
Yeah.
This is a big one. So if you worked for some sort of an oil company, you were chief scientist at BP?
I was chief scientist at BP for 5 years after Caltech. And, they didn't bring me there to help them find oil. All right? They knew how to do that really well. I was brought in to help figure out what beyond petroleum really meant. And that was renewables and alternatives to oil and gas.
Okay, so clearly this guy is very smart, and he has the right sort of qualifications to sort of look at the science and dissect and criticize it. So I think this is somebody worth listening to, actually, worth engaging with. This, whatever criticisms this guy has, I think the scientific community and journals and things like that have to take seriously and address it. And so that's kind of what I want to do here, is kind of look at his arguments and see what merit there is in them, see if he has any points that are worth looking at. And the point about the criticism about working at BP, I think, is fair if you want to talk about biases, in that everyone has biases, right? And so it's clear that working for a company means, at least implicitly, you support their mission and their goals and what they're doing there. I don't think it necessarily implies that he's corrupt or anything. Of course, BP only would hire scientists like this, that supports their vision and supports their business, but it doesn't mean that he necessarily changed his views in order to get that position, to get the money from them. I think that's probably an unfair criticism.
And what I'm going to show you is a record of the height of the Nile River,
Okay.
which has been compiled by the Egyptians. We go to the next. There we go. So this is the height of the Nile River from 640 AD up until 1450 AD. So about 800 years of data every year about what was the lowest level that the Nile River reached in that year. The Nile was important to the Egyptians, as you might imagine, and so they measured it pretty carefully. And what you see are two things. The blue spikes are the annual values. They go up and down a lot. 1 year it was up at 6 meters, 20 feet, and then the next year it was down to 1 meter or something like that. So a lot of variability from year to year. But then if you look at the curve, which is the average trend over 30 years, you can see, for example, in the first 100 years, it was going down. And you can imagine some medieval Egyptian climate panel saying, new normal, new normal. We got to do prayers and sacrifices. And of course, if they just waited another 100 years, it came back up again. And this was all before humans had any influence on the climate.
This is sort of the first evidence that he shows to go against climate change. And what he's doing here is, I guess, using the Nile River as a proxy for climate, showing that there's these natural things in the environment that fluctuate over time and even hundreds of years, certainly every year, every decade, and even centuries. But this is a weird way of, especially if this is your first thing that you're going to, the level of the Nile isn't like a thermometer for the world. This is totally different, right? This is just one piece. And when we talk about climate change, what we're talking about is the entirety of the globe and all these processes going in. And so when he points to this one piece of data that shows variation, I don't think this is a very good strategy here. It's easy to find the paper where he got this from. And the reason that they were looking at this data in this way was to predict the effects of climate change on the Nile River, not the other way around. They weren't trying to show climate change as evidence through the Nile River. They were trying to show that predictions about the level of the Nile River, which is very important for the people living in that area because they need their water, they need to use it for agriculture and all these things. And they were just saying how hard it is to predict specifically the level of the Nile River based on our understanding of climate change, right? And this is what we see from climate skeptics, right? Or skeptics in general. We have this, so the scientific community puts forth this like very broad and comprehensive theory on what's happening in the world, and it takes into account the entire world. We look at much broader things like the global temperatures, not just temperatures at one place. You'll hear critics sometimes, they'll just say, well, in this state or in this region, the temperature's actually been going down for the past, couple decades. But we're talking about global trends and just picking out these little pieces and saying, well, maybe you can't explain this or this doesn't fit with your trend. It's just not the right way of doing this. And oftentimes these kind of localized areas depend on more than global trends. There can be greater effects from kind of local variables that overwhelm sort of the greater trends in climate. And often scientists study these things, and these are kind of cues to look into when you see something that's abnormal. These are things that scientists go and study, and they often do explain these sort of local disparities from what we see from the global trends, and we can learn things from that. But just pointing out that there's small disparities from the global trends is not the way to go about debunking climate science, I think. The data continues, of course, past 1500, right? We have modern data. So this is more or less the data he was showing, right? This is the Nile flood height then the Nile meter ends here, and then we have data from the last almost 2 centuries, right? And this decline is more dramatic than anything that we see in his data showing the rise and fall of the Nile River over this. So even using his own data, we see a much more dramatic change in recent times. And also, this is some weird sort of, it's not exactly a naturalistic fallacy, but it analogizes to one in the fact that, let's just say mankind wasn't causing all of the climate change that we're seeing. It still poses all of these different risks and potential damages that we would still want to potentially mobilize to do something. So if we can understand that there is something to be done to mitigate the effects of this, we would still maybe want to do that, regardless of the cause of it, whether we were causing it or not. Now it just so happens that we are causing it, so we can kind of have a more direct impact by changing our actions. But it's still kind of a weird way of thinking about this thing.
And one of the things that you could do was to measure how shiny the Earth was. The albedo, it's called technically, whiteness of the Earth. And of course, being curious, we asked the question, well, how was the albedo first measured? And the answer was, back in the 30s, some guy started watching the dark part of the moon. And that brightness of the dark part of the moon is lit by light that is reflected from the Earth, and so is a good measure of how shiny the Earth is. It hadn't been done for 30 or 40 years, and so we started up a program that continues to this day to watch the dark part of the moon to monitor how bright the Earth is. And we just published a paper in August that showed the Earth has gotten a little bit dimmer over the last many years, and so not surprising, it perhaps gotten warmer.
Okay, so right off the bat, we're confusing causation with correlation, right? So his team is measuring the albedo of the Earth, which is an important part of climate and how we think of energy exchange even, right? So the way the Earth primarily is heating up is it's absorbing energy from the sun, and then it's either reflecting it or it's emitting it back out into space. And so the first part of that is the reflectivity, and that's what he's measuring, and that's what he's talking about here. And it's actually a pretty creative way of doing this by looking at the dark spot of the moon, right? So if you think about it, the dark spot of the moon is the side facing away from the sun, so it's not being illuminated by the sun, but it's still getting light reflected from the Earth. And this is actually a very complicated process, because if you think about it, we see the moon waxing and waning as it goes around the Earth, and depending on where it's positioned, you see some amount of the daylight on the Earth reflected back to the Earth. And it's the same with the moon sees the Earth in the same way, sort of this waxing and waning depending on its position and the light that's reflected to the moon. So it's these very complicated cycles that depend on a lot of things. The Earth spins, and you can imagine as you have different parts that are reflected let's say some are more reflective than others. So that'll change throughout the day, throughout the month, throughout the years and the seasons, because snow is more reflective than just the ground, right? So this is a very complicated process. But if you track it over time, you can kind of get an average sense of the amount of reflectivity of the Earth. And this is important, right? Because when we're trying to understand heat exchange or energy exchange, what we want is, if something's heating, that means it's taking in more energy than it's giving off. And so if the Earth is reflecting more light, that means it's going to cool down. And eventually, of course, this reaches some sort of equilibrium. So if the albedo is lower, meaning that the Earth is absorbing more of the light and not reflecting as much of the sunlight, that means the Earth is going to heat up. It'll reach some equilibrium, but in the short term, we'll see it heating. The main problem with this is he's kind of actually reversing the causation, right? So he's saying, well, there are these natural cycles of the Earth. It's losing some of its albedo. It's losing some of its reflectivity. So of course it's going to be warming up, and this is just a natural thing. Let's talk about what's reflecting the light on the Earth. And one of the big ones we see is the polar ice caps, because snow is very reflective. So what's actually happening here is the Earth is heating up and melting the snow, and that's changing the albedo, not the other way around. It's not the albedo changing that's heating up the Earth. Okay, and we've seen this throughout history, right? So one of the dramatic climate changes historically is due to continental drifts, right? So the Earth was very warm when all the landmass was around the center of the Earth, and then as continents started drifting to, let's say, to the poles like Antarctica, and you could have snow accumulating there, that actually changed the climate of the Earth dramatically, right? Because you could now have snow just settling on land, and that's reflecting more of the light. The problem with this is, okay, this is a natural way of creating climate change, but this is on a time scale of continents drifting. This is what we're talking about here when we talk about climate changing on timescales. Most of the time, these changes happen over millennia. Okay, maybe you can compare that to a more dramatic change like an asteroid hitting the Earth, and we've seen that in history too. And the effects that we're seeing now, the speed at which we're seeing them now, is much closer to the asteroid impact than to continents drifting. I took a look at his paper too, and it's quite a well done paper, and it's very pretty. He has great data actually, and so maybe that's where another part of his bias is, because this is even though it's a very complicated calculation to do, it's kind of a very clear where the data is coming from, and you can plot it, and it makes pretty trends, and so you can draw these very clear conclusions from his data. And admittedly, the climate data is not nearly that clean, so maybe that's where some of his bias comes in, where he sees kind of more noisy data than he's used to dealing with, and he dismisses it, so like this isn't something that you can actually derive from this noisy data. When we talk about climate change, and the primary causes driving it is either through reflectivity or emissivity, and so he was talking only about the first one, which is the reflectivity. But the Earth itself, the way it cools itself down, is it emits a lower frequency than light into space, right? And then that depends on the temperature. And when we're talking about greenhouse gases, which is what we're talking about when we talk about climate change, we're talking about the ability of the Earth to emit this electromagnetic waves into space to lose energy. And what greenhouse gases do is they kind of shield that from getting it into space and contain it in the Earth, and it gets hotter, and it will eventually reach a steady state, right? Once eventually the temperature of Earth will get hotter, and then it'll produce more of this energy that can't be contained as easily by our greenhouse gases, and so eventually it will reach this steady state. But as you increase greenhouse gases, you're going to increase the amount of energy that's being contained in Earth, and the Earth is going to heat up, and this is our main concern in climate change. This is the main effect that humans are having. We're creating these greenhouse gases.
And this is one I think I'm going to go public with pretty soon in an op-ed. Let's put it up. This is about Greenland, okay? And the popular image that Greenland is melting, and it's melting faster and faster and so on, all right? This is the official data set for how much ice Greenland is losing every year. And it goes up right until 2021, and it starts in 1900. And what's interesting about this, there are several things. First of all, even though human warming influences have been growing steadily over the course of this, there are a lot of ups and downs. So it says it's got to be a lot more than greenhouse gases at play here. The second thing to notice is that in the most recent decades, at the right-hand end of the chart, Greenland is actually starting to melt less rapidly than more rapidly, even as the globe has been warming.
And this is from 2010 to 2020.
Yeah, correct. And then if you go back to 1930, you can see it was melting just as rapidly in 1930 as it was in the last decade or two. And the human influences were less than a fifth of what they are today in 1930.
Okay, so he's doing the same thing here that he did with the Nile River, except that this is more directly related to climate change, I suppose. But he's taking one specific area of ice where, with global warming, there's a lot more ice in the world than in Greenland, right? We're concerned with the global ice levels. And so he's picking just one area where maybe there's uncertainty in the data and saying, well, you can't explain this very well. To be fair, I think Greenland is one of the places where we actually have better data because it's one of the places where there's the most land ice, except for Antarctica, which we don't have nearly as good a data going back to. You can see this graph goes back to 1900. There weren't so many people going to Antarctica in the early 1900s and looking at the ice as they were in Greenland. But still, so he's presenting this data and showing, okay, look, there's all this variation in this area. And if the climate was changing, as people say, you would expect it to just be this straight upward slope, more or less, with some noise, showing that the ice would be melting, continuously faster, right? That's another thing you have to look at here. This is called a derivative. So this is the amount of ice that's being lost every year, right? And so this isn't the total ice. This isn't the graph of the levels and it's going up and down. If the ice has been losing mass, as you can see, this graph is positive for basically its entire timeline, meaning the ice levels are going down for this entire time, right? That's what we call a derivative. As long as it's positive, then we're having a change. And so, okay, what he's talking about here is the rate fluctuating, not the ice level. So let's just be clear about that first of all. Greenland has been losing ice for more than the past century, okay? Now what he's saying is that we expect the rate to change because if the Earth is getting warmer and warmer, that means it would be not just melting, but melting faster and faster, right? And so he's using this data to show, okay, maybe there's something else going on that we're not so clear about. And he is right about that, right? Scientists study these sort of things. They try and understand what's going on. Why are these glaciers in Greenland melting? And so it was actually really easy to find an explanation for why this was. If you look at sort of where the peak is on this graph in the 1930s and compare that to what was going on in the world at that time, especially in Europe, which was close by, that's when we were at the peak of the Industrial Revolution. If you think back to the 1930s, London was literally just covered in soot. London was just black. There's this famous anecdote, I guess, about these moths in England, where previously to the Industrial Revolution, they were sort of speckled, kind of tree trunk color to camouflage with the tree trunk. And then once the Industrial Revolution started, everything got so dirty and black that these moths actually adapted and became black in order to blend in with their new environment. So we were producing an incredible amount of soot at this time, and that absorbs a lot of light, right? And so you can imagine if this soot is in the air, Greenland's not that far away from Europe, which is, the main place for the Industrial Revolution at this time. They're producing a ton of soot, and this is traveling to Greenland, and this soot is landing on the ice and snow and glaciers there. That's having a dramatic effect on the melting of the ice there, right? And scientists have documented. They go there, you can take core samples, and you can see the effect of time and see what was changing the levels there. And it's pretty clear, if you look at it this way, that this is having a dramatic effect. So with our sort of more modern industries and our energy system, we produce more CO2 definitely, and that's causing the greenhouse effect to increase. But they are cleaner in the sense that we're not burning as much coal, which produces all this kind of soot that gets into the atmosphere and lands on things. So it's not as bad in terms of changing the reflectivity in this way. We're not dumping just ash on the snow in Greenland anymore. So even though the temperatures are rising because of greenhouse, we're not changing it so dramatically in the way that we were. And actually, you can see where it dramatically starts to dip down. Okay, one explanation is the World War, and a lot of the infrastructure in England was, kind of destroyed, so they weren't producing as much. But also, they started passing laws to basically clean up the air around this same time in the early 1950s. To kind of prevent all this ash and soot from getting into the air and making. It was a disaster for the health of people, especially in London. They were suffering from pretty dramatic health impacts from the industries there. So that's just one aspect that we see, and that's a good explanation of something other than global warming causing the ice melt in Greenland. And if you want to take that even further, I think it's a good perhaps analogy to what we're talking about today, where the laws passed in England weren't meant to stop the ice from melting in Greenland. I don't think they cared about that in the 1950s. They did it for their own health. They did it for other reasons. They did it to stop the pollution in their own area, and that's sort of the same that we see with climate change now. Is it's not just the effects of climate change. The CO2 doesn't just affect the climate in terms of greenhouse gases. The pollution from our energy system and the ways that we produce our energy, which in turn produce the CO2, are very bad for a lot of people's health. We see increases in asthma and all kind of other respiratory and pulmonary diseases all across the U.S. and the pollution that we produce, which is the same that produces the CO2, has a pretty dramatic effect on those things.
If it grows at 2% a year, which is kind of what everybody thinks it should be doing and might do, you get that curve. If you assume a 4% impact at the end of the century, or even a 10% impact, you just delay the growth by 2 years or a few years in 2100, 80 years from now, all right? So this is not the climate crisis, okay? The economic impact is projected to be minimal.
And this is the economic impact as the way things stand today, without any major interventions in terms.
That's correct. That's correct. Well, it's done as depending upon how much warmer the globe gets.
Right.
Okay. So remember, the Paris Agreement is trying to hold things to 2 degrees centigrade or about 4 degrees Fahrenheit, which is a few percent damage to the economy, okay, in 2100.
Yes.
Okay. Whereas the economy is going to grow by 2% a year. Right? So instead of 70 or 80 years from now, it being, let's say 400, the U.S. economy, instead of being $80 trillion, it would be $76 trillion or something like that in 2100.
This is another weird argument to me. He's disparaging climate models for being able to predict how much damage there will be in the future, but then he's using it to factor into his economic models as just one part of a model that's even broader and with more variables and more unknowns, and saying the future economy is going to be valued at this much based on these predictions, and our climate predictions are only going to damage it this much. Now he's combining two very uncertain models together and saying, this is not a big deal. You can look at the damage, that it's not going to be that dramatic at all. And I mean, for somebody who's skeptical in some ways about predicting the future of these sort of noisy and multivariable systems, he's putting a lot of stock in the predictions of this model that, supports his view, I guess. So I don't know. This is, let's just say, inconsistent of him to be using this data.
Now, if major policy changes are implemented that are going to shift, like the sales of the combustion vehicles being banned, which is what they're doing in California.
Yep.
Did that pass in California? Do you know?
I think that is the current policy in California.
I believe it's 2035.
Right.
Is
And,
that what it is?
and,
I was looking that up when we started.
and the federal government is pushing for the same policy nationwide.
Nationwide.
Yeah.
Now, is there enough of these minerals that make batteries to...
So what we forget, for people who don't understand energy, want to change the energy system, is that it is a system. And so let's talk about cars, okay? You have to change the car itself, which leads to issues about, do you have enough minerals? You have to change the fueling infrastructure, namely, do we have enough charging points? And can the grid handle all these cars plugged in at once? And then you have to change the fuel, or at least provide more electricity to power the cars, in addition to what you're doing now.
Okay, so I want to talk about this one, not because he said anything wrong here. He actually said quite a lot that was right, I think. But this is sort of my pet interest, I suppose, talking about electric cars, because to me the switch to electric cars is just a no-brainer in terms of the engineering, at least, of the problem. Now, in terms of the political forces and the infrastructure, those are separate things. But yeah, let's just first talk about, I guess, why electric cars are different than combustion engines. And the main difference is electric motors are insanely efficient compared to combustion engines, right? So if you think about, you have a certain amount of potential energy that you're using to power your car, and it can be in the form of electricity, or it can be in the form of stored potential energy, or stored chemical potential energy in gasoline or something, right? And then you have to convert that energy into motion that powers your car forward, right? And electric motors are like 90+% efficient at this. They're insanely efficient. There's some issues with charging and things. Some efficiencies lost when you're charging and discharging the batteries, and that depends on the speed. So all these people who want to charge their cars faster, they're actually losing efficiency when they do that. But that's sort of another thing. But the driving energy itself, the driving power of an electric motor, is insanely efficient compared to a combustion engine, which is only like 30% efficient. So like when we're talking efficiency here, we're talking dramatically different, multiples more efficient by converting our cars to electricity than to gasoline. Okay, and then there's some other issues, of course, when you're driving the car. It's not just the motor efficiency, but the efficiency of the car itself, and that tends to reduce the efficiency of the overall performance of the system by about a third. So if you think about an electric car, maybe is converting electricity to kinetic energy at 90%, and then it's losing a third while it's driving due to wind resistance and things like that. So we're at like 60% efficient, whereas combustion cars are like, the good ones are like maybe 30% efficient at converting gasoline into kinetic energy, and then a third off from there is like 20% efficient. Like a good car is about 20% efficient at converting gasoline. So this is really bad, right? This is something we should have tried to do years ago. My personal bias here, I think they've ruined a lot of our cities. That we should have invested in more public transportation versus using these cars to commute. This is my bias, but I think the car was just a bad thing for us to build our entire country's infrastructure around, and we should have been pushing for this a long time ago. But he's right here that you do have to change quite dramatically our infrastructure, but it's got to be done at some point anyway. This is like, you see other countries doing it. This is the future. The reason also to change to electrification of our transportation system is most renewable energies are directly creating electricity. So we do use fossil fuels to create electricity now, and that's also what we're trying to replace when we're talking about renewable energies. We're trying to convert fossil fuel creating electricity to renewable sources of creating electricity. And that's actually an interesting place to go too, is that when we talk about efficiencies of renewable energies and efficiencies of, let's say, fossil fuels for creating electricity, these power plants for creating electricity using fossil fuels are not that efficient either. They're better than cars, but they use sort of the same process of burning a turbine. They're less than 50% efficient. These systems are in fact tied together, like he says, and changing one means you're going to have to change the whole system. But we see benefits in changing each one of these systems. They're all tied together, and we see the benefits of changing sort of all of these systems together. They all fit together, and there's a clear path forward that we can see. And this is something we can do if we just decide to. And as long as gas is cheap, it's not going to happen by itself. So we do need the government to come in and make laws to kind of push the market forward into these spaces. And I think saying a car ban in 15 years is not a dramatic thing to do. 20 years ago, I think we should have said, okay, in 20 years, no more electric cars, at least not in cities, because they pollute a lot. We didn't even talk about noise pollution. That's another thing. It's not just the chemical pollution from the smoke and the combustion, but like noise pollution in cities is really bad. And electric cars are great. They're very quiet. To me, if he's not supporting something like this, then I feel like he's just not willing to use the government to sort of promote these policies in any sphere, really, from what I can tell. And I've listened to this whole podcast already, and he doesn't make any specific prescriptions for changes that we can do that are, I guess, reasonable, realistic for having an impact on our greenhouse emissions.
The second is it conflates carbon pollution, and I hate that word because CO2, which is what they're talking about, is essential for plant growth. The more CO2, the more plants grow. All right, so in that sense, it's not at all.
Is that an
pollution.
inconvenient truth?
Yes, that's, and you know, the Earth has gotten 40% greener since 1980.
Yeah, I'd heard about that from Randall Carlson.
Yeah,
who explained that to me, and then when I saw it's actually in your book as well.
Yeah.
Okay, I really dislike the way that they're framing this thing. It's true that carbon dioxide is an essential part of the atmosphere, and increasing it increases plant growth, right? That's one of the effects that CO2 has. Okay, let's draw an analogy here. You need calories to function as an animal, as a human, right? And if you increase the amount of calories that you're eating every day, you're going to get fat. There's some equilibrium that's important to have, and it's not just more is better. That's definitely not the right way of looking at this thing. You can't just increase and be like, oh, look, you need food, so more food is better. More food is not better in all cases, right? It leads to a lot of health problems, and that's what we see with climate change. Okay, there's some amount that's all the organisms, all the plants and things have adapted to in the environment, and so some amount of carbon is important, some equilibrium amount that they can adjust to and use. When you increase that, and we've increased it a lot, that is hard to adapt to, and it's going to cause a lot of problems. So just saying that CO2 is good for this thing and more is better is definitely not the right way to look at it.
What's going to happen as people start heading in that direction is that, and with other emissions reducing measures, is there's going to be popular pushback. People won't be able to buy the kind of cars that they want or need, actually. They're going to see their electricity rates go up. They're going to see the grid becoming less reliable. Certainly a phenomenon you know about here in Texas. And they're going to say, tell me again why we're doing all of this when the U.S. is only 13% of global emissions?
Yeah, and this problem with the grid is another issue that I have, where right now we have these sort of big centralized power plants, and then the energy distributes from there, and they travel long distances. The future grids that people are envisioning are much more dispersed, much more distributed sources of power, so that if one goes down or one connection gets bad, that it's actually much more resilient, I think, than the system we have now.
I believe that that's what's going to happen in this country because they're pushing too far and too fast. I like to say you need to change the energy system not by tooth extraction, but by orthodonture. Slow, steady changes.
Sure, but he doesn't even propose any small changes that we can take. I think what he means here is the slow change that will naturally happen in a market, meaning that the government shouldn't get involved at all in creating these sort of dramatic steps forward.
Now, how do they shape the models? Like, how do they construct them?
Boy, the model, so projecting the future more generally is very complicated. First of all, you got to say what emissions are going to be going forward, and that depends on technology and regulations. But even given some scenario for emissions over the next 80 years, you got to feed that into a climate model, and you use that to predict the temperature and other changes in the climate. The climate models cut the Earth into zillions, hundreds, millions of cubes that cover the Earth. They go up into the atmosphere, 20, 30 layers of cubes, and then down into the atmosphere, down into the ocean, 20, 30 layers. Okay? And then the models use the laws of physics to move water, air, energy, light, and so on through these cubes, 10 minutes at a time, typically. Okay? And you do that for centuries, so millions of steps in time. There are a number of fundamental problems in doing that, but let me just highlight two of them. One is that the boxes are typically 60 miles on a side. You can't make them smaller because then you got too many boxes and the computer can't follow them all rapidly. And on a 60-mile scale, there are a lot of things that happen in the weather that are much smaller than 60 miles. How many clouds are there? Are there thunderheads? Is it raining? And so on. And so you have to make assumptions about, given the temperature in the box and the humidity and so on, how much clouds are there? What kind of clouds are there and so on? And different people make different assumptions. And so you get different answers coming out of the models. That's one. Okay. The second is the models, human influences are physically very small. The flows of sunlight and heat in the climate system are measured in hundreds of watts per square meter. The human influences are 2 watts per square meter. And so the model has to be very precisely balanced if you're going to see the effect of human influences, balanced to about 1%. Right? And there are different ways to getting that balance, to tuning the models.
So what he's talking about here, he's specifically criticizing climate models, which is what they use to predict, sort of the specifics about, let's say, sea level rise and things like that, and temperatures in different places. And that's a very, very complicated process, like he describes here, and it's not very let's say reliable. But he hasn't mentioned at all sort of the other, I guess, fundamental underlying physics that go into just warming the earth, right? He hasn't talked much about greenhouse gases, or he talked about his albedo measurements, but didn't say what that does so much. And that's important to understand, because there's some pretty simple fundamental physical principles that go into understanding just the general heating of the earth, right? If you start changing the way that the earth absorbs and reflects energy, and you change it in a way where it's containing more of its energy, it's going to heat up, and that's just a basic physical thing. And so the models are, of course, very complicated, because the way energy is distributed along the earth is a very complicated thing. But there's some basic things that we understand about this process, and just heating it up, we know some things are going to happen. We know ice is going to melt, right?
So these people that think that there is an established, settled climate change, what are they pointing to?
They point to the global temperature rise.
Global temperature rise.
And then they'll point to things like Greenland melting, of course, which we've seen is up and down and kind of not driven by human influences. Right? But they'll point to the temperature rise. We could pull that up if you want to see that. Let's do that, okay? And I think this is something it's one of the first charts in one of the files.
Which number is it?
I'll tell you in one moment.
Is it?
Yeah, that's it. Great. Okay. So on the left is a measure of the global temperature. It's not the global temperature itself averaged over the globe, because we don't know that number actually very accurately. No, we don't know it to within a degree centigrade or so, maybe a bit more.
When did we start knowing it?
Well, we know changes. It's easier to know changes. And you can see this graph of changes in the global temperature averaged over the globe starts in about 1860. This is data from a project at Berkeley led by my friend Rich Muller, whom I helped get this project funded and off the ground. And what you can see is that the data show up until about 1920, from 1860, it wasn't doing very much. And then the temperature started to rise in about 1910. It went up by about half a degree to 1940. It then actually went down a little bit until 1970, and then it started to go up again. And it's been going up now.
Okay, this is the same problem we had before with the Greenland ice melting. What he's showing here is not the temperature. Again, he's showing the change in the temperature. And as long as that line is above zero, that means the temperature is increasing, right? So that means since, 1930-ish, that means the temperature has been increasing ever since then. When he says it went down a little bit in the 1960 or so, he just meant the rate went down. It was still increasing in temperature, but just the rate of the increase in the temperature was the same, meaning the temperature was going up at the same rate, okay? And then it started speeding up again into, the 21st century.
And what's interesting about this graph is, first of all, you can see that the rise has not been steady, that the rate of rise from 1910 to 1940 is about the same as the rate of rise from 1980 to 2010. How could that be? And in fact, it was even cooling from 1940 to 1970. How could that be if human influences have been growing steadily since 1900? And the answer is, they don't know.
So again, he's kind of just trying to put some shade on the explanation here by they don't know exactly how this one aspect of this graph works. So you can dismiss the whole thing, even though the whole thing is increasing. And there are explanations that people have, sure. That's what climate scientists study. He's even mentioned things like how ocean currents affect this and how heat can be stored in different places in the earth that isn't necessarily in the atmosphere or on the surface of the ocean, or things that we're sort of easily measuring. Heat can be stored, let's say, in melting ice, right? We talked about that. You can put heat into a system and not change the temperature, but you can melt the ice. And that's a change that we see. And like he said, these are complicated systems. So the effect of increasing the temperature on the system may not be linear all the time. We may see these different changes happen in different parts of the world and may impact in different ways. And that's what scientists study. They talk about all these different things and they compile all this data. And so it's not just one little thing here. It's not the global temperature is a very good evidence for it, but they look at the evidence throughout the entire world and say, okay, this is happening. Why is this happening? Probably because of a temperature increase. Why is this happening? And we see all these things when you combine them together. That's what we're talking about when we're talking about global climate change. And this guy just likes to pick little things and say, okay, well, if we're expecting global climate change to be heating, then we would expect this here, and we don't see it. So, maybe it's not right.
13 senators, led by Mr. Schumer, proposed a bill that says the government may not spend any money to challenge the consensus. The Council of Trent in the early 16th century said very much the same thing about church dogma. Not about spending money, but you'd be in all sorts of trouble if you challenged dogma.
What would possibly motivate the government to come out with a statement like that they can't spend any money to challenge the consensus? And doesn't a consensus mean most? It doesn't mean all.
Oh, right.
So in cases of dogmatic opinions or ideologically formulated opinions...
Yeah. I'm so surprised that the government would try to suppress the scientific process like that.
Okay, this one I had to look into, right? Because this seemed silly to me that they would do this. Because the way science is funded is not through these sort of blanket proposals that say you cannot do this from the top down. That's not how these things happen. This surprised me that he would even say something like this. So what he is referring to here is the creation of a committee under President Trump, where they were basically going to promote not the science, not fund the science, but fund the sort of dissemination, the communication of this climate skeptic information. And this is a political institution, right? This is not a scientific group that's meant to study something. This is a political group meant to promote some sort of ideology or something to the media, right? And the guy they picked to do this is a famous climate skeptic from the 90s. Even he goes way back. This guy was he was a holdover from H.W. Bush into the Clinton administration as director of the DOE, and he got fired by Gore for fighting his measures that he wanted to take on ozone and the ozone layer and the problems that we were having with pollution destroying that in the atmosphere. So this guy's kind of been in the business, I guess, of climate skepticism for a long time, and I guess currently now he's the director of something called the CO2 Coalition, which is an organization that's dedicated to touting the benefits of CO2, and this group is funded, of course, by energy executives and hard right foundations like the Koch brothers and Mercers and things like that. It wasn't an explicit law to block all funding to climate skepticism or something like. I don't even know what that would mean. There's a quote from Schumer that I'll just read because I think it sums up his opposition to this very well. He said, "This is a fake climate panel. This is the intentional, deliberate sowing of disinformation about climate science by our own government and will not stand. My colleagues and I are introducing legislation to block funding for this farce and make sure that the fake news stops here." Right? So it's clear that this is just a political stunt by the Trump administration. And I'm kind of amazed that he's saying this actually here, because it seems very partisan for him to promote this view to me. And his image that he's presenting as just this sort of neutral arbiter, follow the science guy. In this case, I really kind of question his motivations for bringing this one up, because not only is the panel that he's promoting here very clearly propaganda promoted by the Trump administration. The way he sort of presented this as sort of a blanket government statement, which isn't what happened, makes me think that he's operating in kind of bad faith. Okay, so to wrap things up here, then, I think what we've seen from this presentation is a somewhat fair critique of the climate scientists, at least in a lot of the places. I think he presents ideas that are worth considering. Some that I think are drawn from personal bias towards the oil and gas industry or the energy sector. I think those are biases and points that need to be dealt with. So, some of the times I think the bias kind of shines through and becomes almost the point of bad faith. But I think generally this is a perspective that is actually valuable. I guess what I'm saying is that it shouldn't be suppressed in any way. I think this should be discussed, and that's what I'm trying to do here, is try and look at the arguments that he's presenting and maybe point out some of the flaws in his thinking. And I definitely encourage everyone to go watch this full video, and then Joe Rogan has another guest on afterwards, who's a scientist from Texas A&M, and he really breaks down sort of the underlying science of climate change in a really, really good way, much better than I did here, actually. So I definitely recommend going and listening to that if you're interested in learning more about the climate and seeing some of the science and the reasons for concern that we have with respect to climate change and our understanding of the science that we see today.